Good evening, ladies and gentlemen, and welcome to the PATCA evening event. Tonight, we're fortunate to have Walt Maclay, president of Voler Systems, give us a briefing on digital biosensing for wearable devices and how to power them. Walt?
Well, thank you, Sean. So let me start right in, and feel free to ask questions that have brief answers during the talk. If you want an extended answer, we can wait till the end. So I'm going to talk about some common physiological measurements. These would be measurements that you typically find on a wearable device. And they have, I'm going to talk about their capabilities as well as their limitations. And then with wearable devices, battery limitations are always a major factor. And then I'll talk about saving power. So wearable devices have a lot of uses. Some people are using them for lifestyle choices, for tracking their own disease, for tracking exercise and weight loss, or general monitoring. They're also used to track people in a hospital to keep track of their health instead of having a nurse come by several times a day. There are even doctors or drug companies that use wearable devices to monitor the effects of drugs. But what's really interesting is in 2020, during the pandemic, remote patient monitoring became the standard. And this happened because, let's see, I'll go to the next slide. In remote patient monitoring, last year, payment codes were put in place so that you could get reimbursed for doing it. And the FDA put in place some emergency regulations that made it a bit easier to implement remote patient monitoring. So it has become the standard because people, the doctors, the healthcare workers need to keep track of patients, and they'd rather not have them come into the office or the hospital. So the human body is very complex, but there's a lot of data. And let's talk about a few examples. These are some of the leading uses of wearable devices. Cardiovascular monitoring. And for that, you're going to measure heart rate or ECG, the breathing rate, blood oxygen, and even motion. Sleep monitoring is another big one. And you want to monitor blood oxygen, body temperature, heart rate, and again, motion during your sleep. For diabetes, you want to measure glucose. And in some cases, you're operating an insulin pump. And in the hospital, there are wearable devices that are typically stuck on your abdomen that will measure many parameters. So I'm going to talk about 8 different types of measurement. And at the end of this, you'll be experts in these types of measurements. And the first one is very simple, measuring temperature. There are lots of simple ways to measure temperature. It's easy to do. But it's not so easy on the body because what you really want to measure in most cases is the core body temperature. And the core body temperature is not measured very accurately on the skin in most locations. It's pretty good on the forehead. It's pretty good under the arm, but often wearable devices are on the wrist, and that's a pretty poor place to measure temperature. If you go outdoors in a cold day, when you come back in, your wrist is not going to be at core temperature. If you're exercising heavily, it might be quite warm, but if you're sweating a lot, it may cool down quickly. So it's hard to predict. However, you can use algorithms to adjust for this. If you keep track of the motion of the person, the ambient temperature, as well as the skin temperature, you can do a pretty good job of predicting when you should pay attention to that temperature and when it would be close to the core body temperature. One other thing about body temperature, the contact is important. If you have poor contact, you do have heat flow. The body is typically a different temperature from the environment, and the heat flow you have to have good contact, or you'll have a large temperature difference between the skin and the temperature sensor. Motion is another sensor that people are very familiar with. They've been in use on wearable devices for a long time. They're for measuring step counts. They also measure gait analysis, which can be used to measure illness. They're good for measuring all types of motion or lack of motion, such as walking, standing, or sitting, and even for dead reckoning. So if you've got a 9-axis motion sensor, you can keep track of what direction someone's going, how far they went, what speed they were traveling, and so on. And the devices can be put on almost any part of the body. What's really cool is the manufacturers of the motion chips have created algorithms. They've got teams of programmers writing algorithms that allow you to do many of these measurements. So for example, step counting is done with a device on your wrist. If you think about it for a minute, how do you measure step counts on your wrist? It just doesn't make sense, but they're able to do it because they have a clever algorithm. And the same thing with measuring whether you're walking, standing, or sitting. The device could be on your wrist or it could be elsewhere on the body, and you're able to make these measurements because of the great algorithms that have been created for you. Heart rate, of course, one of the common measurements. It's often done.
I'm sorry, we had a question on the last slide.
Oh.
What are the 9 axes of motion?
Good question. Typically, originally, a motion sensor was acceleration, and there are 3 axes, so you would have a 3-axis accelerometer. What's been added since then is another 3 axes of gyroscope and 3 axes of magnetometer. The magnetometer measures the orientation of the Earth's magnetic field. So you know what direction you're pointing. The gyroscope is excellent for measuring how far you've traveled, or also for orientation. And the accelerometer, you combine them all and you've got a great way of measuring where you are. So one way to measure heart rate, a very common one, is with ECG electrodes. And all you need is 2. They've got to be far enough apart and they'll give you a good measurement. Now, measuring on your wrist doesn't work very well. In fact, if you have 2 electrodes just on your wrist, it doesn't work at all. So how do you measure heart rate using the ECG electrodes with a watch? Well, it only works if you reach over with the other hand and touch a spot on the watch. And now you're actually measuring very different, very widely separated points across the chest. So that's a limitation when you're using ECG electrodes. Another common way of measuring heart rate is with a pulse oximeter, or at least with a portion of it, the PPG sensor. The pulse oximeter is more sensitive to the heart rate than it is to the oxygen content. And in fact, it has to subtract out the heart rate to measure the oxygen. So it's very good at measuring heart rate. And there's 2 types, the transmissive, which sends light through the finger or through the ear. And there's the reflected, which sends light into the body and looks at what comes back. It works in all the other places in the body, but the signal is smaller. And then you can actually measure heart rate with a pressure sensor. You do that yourself when you put your finger on your wrist to measure your pulse. It can be done, though the other measurements are more reliable, so it's rare. And now let's talk about blood oxygen, since we're talking about the PPG sensor. And don't ask me to say the word. The PPG stands for something like plethysmography, I think. I rarely can say it. So you're looking at oxygen saturation in the blood, and the only way that it's done is with a pulse oximeter. The pulse oximeter puts in 2 different infrared wavelengths, or actually they're not always infrared, sometimes red, sometimes even green. It takes the difference between the 2. Both of the signals are affected by the pulse, because the amount of blood that is being seen varies up and down as the heart beats. If you subtract out the two, what's left, one of the signals is sensitive to the hemoglobin and one is not. So the remaining signal is a very good indicator of the saturation of the blood. And I mentioned you've got the transmissive type and the reflective type, where the reflective is the one people want to use because it's convenient. It works almost everywhere, except not so well on the wrist because there's not so much blood there. It takes quite a bit more work to get the reflective type to work because the signal is small. So you have a lot of noise and a small signal, which if you're an electrical engineer, you know that's a difficult thing to overcome, but there's lots of algorithms dealing with signal to noise ratio, so it can be done. But the transmissive only works on the finger and the ear, where you can send infrared light through the body. Now, ECG, EMG, and EEG, it's all measuring electrical signals generated by the body. ECG, the measuring of the heart. Now, the standard is 12 leads. If you go to a lab or a hospital, you have a healthcare professional make an ECG measurement, they're going to use a 12-lead ECG. There are devices now with just 2 leads that give results almost as good as the laboratory devices. But you've got to be careful that they're spaced far enough apart. And I'm saying here 1.5 inches, that's when it's on the chest. If you place it elsewhere, it gets to the point where you can't make a measurement. So as on the wrist, for example. EMG is electromyography. This is measuring the movement of muscles, or actually the signals that go to the muscles to make the move. One common place to make this measurement is on the wrist or on the arm, where you can measure which muscle is moving to the fingers. And there actually are devices that you strap onto your wrist, and you can move your fingers like you're typing, and it knows what you've typed simply by measuring which muscles are moving. Now, if you miss by a few millimeters, you'll pick up the wrong muscle. So the positioning of that band is very important. And you know, those muscles are very close together. Your arm doesn't come with a great reference, so it can be a bit tricky to get it accurately placed. The EEG, the electroencephalogram, is measuring your brain waves, and you can't pick it up anywhere except on the head. But there are devices that have measured on the temples. If you're wearing glasses, you can put electrodes on the temples pretty easily. It would also work on the forehead, but wearing a wearable device on your forehead is a little awkward. And there are helmets that have probes that will go through the hair that have been very successful in picking up signals, the EEG signals. So these measurements have pretty good success. One thing that I didn't mention here is on a wearable device, you'd like to have a dry electrode. Putting on the wet electrodes means each time you put the device on, you've got to get this electrode out. It's a little bit, it's wet. It's not so convenient. And it's going to dry out over time. It's much better if you just put the thing on and don't worry about the electrode. But dry electrodes don't make as good contact. They are successfully used. We've even worked with dry electrodes in pants that are able to measure the ECG signal while somebody's running, which is tricky. It takes some good signal processing, but it can be done. Respiration rate is another important parameter. There's several ways to measure it. One is with a chest strap. This has been the standard for many, many years. But if you're putting on a wearable device, a chest strap is a little inconvenient. So people are looking for better ways. A nasal cannula is a common way that it's done in a hospital, but putting a device in your nose it's uncomfortable. It's certainly not a convenient wearable device. So the gold standard that people are trying to meet, and it's not easy, is the thoracic impedance. You can put a device on the chest that measures the impedance across a portion of the chest. And as you breathe, the impedance changes, and it can be measured quite well on the chest. By the time you get to the wrist, it's very difficult to measure because you've got the arm in series with the measurement, and the resistance or impedance of your arm is much greater than what you measure on the chest. So it's a very small signal. And yet there's one more way to measure respiration. People have done it by just measuring the ECG. You filter out the heart signal. So you filter out a signal that's on the order of 50 to 100 beats per minute. And the slower signal is kept, and that's respiration. It seems to work pretty well. Blood pressure is a more difficult one. You'd like to have a device you could mount. Well, the most common place people put these things is on the wrist, though other places are common, even the ears these days. Measuring with a cuff on your arm is not very convenient. It's bulky and it uses a lot of power. You can put one on your wrist. The ones you wear on the wrist are not as accurate. So what people are trying to get to work is pulse transit time. With pulse transit time, you're measuring the time difference between the electrical signal generated by the heart and the actual pulse when it arrives at the extremity. So it sounds like this should work really well on an extremity, like on the wrist. The difficulty is that it varies from person to person, and it's difficult to get medically accurate results. There are companies that claim they have achieved it. They've done a lot of different testing on a lot of different people, particularly with different colored skin. The skin color can certainly get in the way of getting the same accurate results for everybody. So it looks like this is something we're going to be seeing more and more. And it works quite well in the ear, apparently. And one other way to measure blood pressure that I've read about is using the ECG signal. This was done in a laboratory, university laboratory. They didn't describe exactly how they did it, except with the neural network, and it was not medically accurate. So finding this in a commercial device, it's a long way off. Measuring glucose has become very common now. Wearable devices often use microneedles. Now, microneedles sounds like it would be uncomfortable, but they actually feel like rough sandpaper. It doesn't feel like needles. Then there are devices that actually have a single needle that actually goes under the skin, and they're surprisingly comfortable. My wife uses one. But there are also implanted devices. So you got a number of ways of measuring blood sugar with a wearable device. The ones with microneedles need, frequent calibration. They need daily calibration. The one that has a needle that goes through the skin does not need that, but even there they ask for one calibration during the week in which you wear it. The implanted ones don't need calibration. They have issues of, I don't know if I want to put something inside my body, and then powering can be a problem. Now the fingertip is the standard for making this measurement. Putting something on your finger is inconvenient because your fingers are used for everything. Also, you're trying to avoid the pain of, what's the word I want? Cutting your finger. So the devices are put elsewhere, often on the shoulder or on the abdomen, and they seem to work quite well there. But again, the wrist is a very poor place for this one as well. So when you think of a wearable device, the first thing you probably think of is a watch, and there are a lot of smart watches, and they have a lot of physiological measurements, but it's difficult. It's the most difficult place to make these measurements. And now with pumps that you can wear, you can have the pump connected to the glucose measurement, and you've got an actual external pancreas that'll maintain your blood sugar. It's we've made a lot of progress there. So as you can see, not all body locations can give you great results. I've mentioned that the ear is a really good place. One reason it is good is because you can look at the eardrum and it's got great visibility of the blood. But another good reason is people are wearing earbuds a lot. And if you're already wearing an earbud and you add a physiological sensor to it, that's very convenient. It's a lot like the wrist. If you're already wearing a wristwatch, getting a wristwatch with more sensors in it is very convenient, but it's one of the worst places. So measuring on the leg, if you're on the calf muscle, that's a great place to have good blood flow. But when you're running or jumping, the shock that you're measuring can interfere with some of the readings, in particular a PPG sensor. The forehead is an excellent place for a lot of these measurements, but not such a convenient place for a wearable device. You probably don't want to go out in public with a device stuck to your forehead. The arm is pretty good, and it doesn't mention it here, but under the arm is very good because it's great for temperature, and there's also pretty good blood perfusion in that area. And then the ankle is very similar to the wrist, with the additional problem that it has a lot of shock when you're moving. So let's switch over and talk about batteries, because all of these devices require batteries, and it's a major design factor in every single device. So batteries, why don't they get better? They've been changing very slowly. If they changed as fast as semiconductors, you'd have one the size of the head of a pin. It would power your car and you'd pay 1 cent for it. And you know that you're not even remotely close to that. And we'll never be that close. We're dealing with the limitation of chemical energy storage. So we're going to have to work around the limitations of batteries. Chemical energy storage, we're approaching the limit. And I don't think we're going to see nuclear energy on a body, on a wearable device. So people are doing a lot of research to improve the energy density, but if we're approaching the limit, it's not going to go fast. I suspect that in a few years, you'll see maybe 2 times the density. But I said this a couple of years ago, and it has hardly changed at all. So by comparison, and by the way, this is a logarithmic graph, not linear. Alkaline batteries compared to lithium, the rechargeable ones, it's about a 2. In fact, lithium is 2 times better. The lithium replaceable is 2 times better than the rechargeable. And gasoline has 10 times the energy storage capacity of lithium, but it has a safety problem. So as energy density has increased, safety has become more of a problem. Every lithium battery requires a safety circuit. And even with the safety circuit, if the battery isn't designed well, it can catch fire. And Samsung, a very reputable company, had a big problem with this. And we've also heard about other problems with batteries, particularly on the boards, not skateboards, but the other kind of boards. Even if you can't ship a lithium battery by air unless it has a safety circuit. So shipping of a box of lithium batteries just to a manufacturer can be a problem. So one solution to this is use energy harvesting. You can pick up energy from the environment. You can get energy from motion of the body, temperature differences generate energy, and even from radio frequencies. There's a major limitation with energy harvesting. Everything that's available, with the exception possibly of photovoltaic cells, generates microwatts. And in just about every device that we've been asked to design, they consume milliwatts. Now, you may be able to reduce the size of the battery, but if you're adding the cost and size of the energy harvesting, the trade-off is, it's an improvement, but it's not a big improvement. So for this reason, it's rare that energy harvesting is used in wearable devices today. Now, photovoltaic cells can generate a lot of power, but only if they're pretty large. You know, you can power your house from something on your roof, but you're not going to put it on your body. I've been told about devices that I believe they're generating power from the motion of particles, just the heat motion, picking it up from the environment, that theoretically can do tens of milliwatts or 10 milliwatts, but nobody's actually produced one yet. They're in the microwatts as well. So there may be an improvement here, and we'll see. So if power is a major factor and batteries are not going to improve, what's left is we'll improve the electronics. And I'll talk briefly about all these areas. With wireless communication, you've got to make a trade-off. You can have very low transmission power, but you can't have a low transmission power with a high data rate and a long distance transmission. You're going to have to give up one of these. Well, fortunately, most wearable devices don't need to transmit at high data rates. If you've got a video camera, that's a pretty high data rate, and you're going to either have a big camera or very short time that it transmits. And there are a lot of different standards that make different trade-offs on these three things. So because of this, there are three different ways that data gets into the cloud from a wearable device. One is to go directly to the cloud, but this means you have to go several miles, long distance. So what's been traditionally done is to use a gateway from the device to a gateway to the cloud, a gateway, for example, like Wi-Fi. Or the other one you can do is from the device to a mobile phone to the cloud, and the mobile phone is essentially a gateway. And with a mobile phone, not far from the device, you can use Bluetooth LE, which is very low power. So it's very popular. So let's compare various wireless types of communication. I'm going to show you a chart where across the chart, the data rate increases, going down, the distance increases, and the numbers are the power. So a lot of data here, but in the upper left corner is very little data being sent a very short distance. And clearly Bluetooth LE or Zigbee are going to give you the best. They're 150 microwatts if they're continuously running. And of course you can turn them off. By the time you get down to the lower right, you're dealing with long distances and higher speeds, in some cases video speeds, and you're approaching a watt. So what's interesting here that you may not have heard about is LoRa, L-O-R-A, which you can see in the upper right, or sorry, the upper left, and it goes all the way down to the 1 kilometer. I apologize, the LoRa is 30 milliwatts. It's the number's misplaced in the lower left. There's also Sigfox, which is a similar long distance communication at low power. There's also NB-IoT and LTE-M, which can go a long distance at low power. You'll see that NB-IoT and LTE-M can even go at a fairly high speed, but there's no advantage in power. So that's not really what they're intended for. What I should point out is in just over a year ago or so, NB-IoT and LTE-M got installed in enough cell towers that you could reach more than 90% of the US population. So although these technologies have been around for years, it's only in the last year or so that they've gotten placed enough places that you can actually design a device and have it work for most people. At over 90%, it's approaching the availability of a cell phone. So let's talk about displays. Now, a lot of wearable devices don't have a display. That's a great way to save power. If you send the data to a cell phone and display it there, the cell phone has a pretty big battery and everybody's used to charging it every day. But if you do have a display, a plain old grayscale LCD is definitely the lowest power. You can go to a color LCD with a backlight or an LED, and they can show you great colors. They can show motion, but they use a lot of power, from milliwatts to watts. Digital paper is a really good alternative. The issue with digital paper is the color is poor, so it's mainly for black and white. It's slow, it doesn't display video. Those two are limiting it quite a bit, but for a reader, it's perfect. While you're reading that page, there's no power. It only consumes power when you change the display. The prices have been somewhat high. They should be going down, and you're starting to see digital paper, but it's not really big yet, except for the readers. So let's talk about the sensors. We talked about sensors in every respect except power. So I mentioned cameras in the upper left here. The camera chip itself draws on the order of 150 milliwatts. These are typical numbers. They obviously vary from device to device. But if you want to add illumination, you may draw another 200 milliwatts. So cameras are far from low power. GPS at 20 milliwatts, I would call moderate power. And that's why you often will use GPS to find out where you are and then turn it off and use a 9-axis motion sensor to track for several minutes until it becomes inaccurate, and then turn the GPS on again and find out where you are and correct the position from the motion sensor. The pulse oximeter at 10 milliwatts is moderate, but you don't have to measure your blood oxygen continuously. You can turn it off, and turning it off, which is the function of software, is a very important part of a wearable device in low power. A pressure sensor can be all over the place, quite low at 50 microwatts to moderate at 50 milliwatts. Measuring EKG or ECG and heart rate on the order of a milliwatt. So this is getting pretty small. 9-axis motion sensor, less than a milliwatt. Microphones, they've got quite a range with different technologies, but they can be well under a milliwatt. And light intensity, similar. But the best one is the 3-axis accelerometer, which is in the microwatt range, as little as 10 microwatts. And this is when it's on. You can turn it off and it's much lower. So because of this, and because they're low cost, an accelerometer is often used where it's left on and everything else is turned off. If there's motion, it can turn on the processor with an interrupt. The processor can quickly look at some other sensors and decide if there's an event that needs to be monitored or if it's the time to do a measurement. And then if it isn't, it quickly turns off. So this is a great way to save power. So let's take a little look at microprocessor power. There's a huge range of power that's dissipated depending upon the processor chip that you buy and the software that you run on it. So if you're running at a low data rate, this is maybe seconds or minutes between samples. And well, you can have a power consumption of 1 to 10 milliwatts. And this is running continuously. This is not turning it off. If you're doing audio compression, you're going to be another order of magnitude higher. Video compression, another order of magnitude higher. It's starting to be quite a bit. And of course, if you've got a multiprocessor running Windows, you're in the many watts. So that's clearly not going to be on a wearable device. And video compression would only be used on a device that's taking continuous video with a camera. But you can see why the battery has to be pretty large and the time frame that it's running has to be pretty short. So if we summarize all this together, let's just give an idea of what you can achieve, including the sensor, the processor power, the display, and wireless. So at the low end, and this is in the 10 microwatt range, let's say we've got a 3-axis accelerometer. The processor is asleep most of the time. There is no display. And when it does wake up once an hour, it sends the data by Bluetooth LE. LE stands for low energy. And it just sends it to a phone. You can do this for a year on a coin cell. So it's a lot like what you get with your watch, with the plain old watch, not the one you have to charge every day. A medium power, now we've jumped 2 orders of magnitude more. If we're turning on a GPS sensor every minute, the processor is running a lot, making decisions. It has an LCD display, but no backlight. And it sends data by Wi-Fi once a minute. This could run for 2 months with one AA battery, an alkaline battery. Now that battery is kind of large for a wearable device. But 2 months, that's pretty good. Or obviously you could run for a day on a much smaller battery. And then at the high end, and this would not be a wearable device, except this could be a cell phone, which you may put in your pocket, you might call it wearable. It's got a whole bunch of sensors on it. It's got a very powerful processor, a color LCD display that can show video very well. It's got a backlight. It may have Wi-Fi connected all the time. Cellular is maybe connected all the time. If you're running all that all at once, you're lucky to last for a few hours. It won't last all day. And you're on the order of a watt. So it gives you an idea of what you can achieve with different situations. Now, one thing that you give up when you're going for the really low power is the latency is long. And this is talking about if I tell the device I want it to do something now, well, in that low power example, it only turns on every hour. It's not going to respond for an hour. And in most cases, if I want the device to respond to me, waiting an hour is not acceptable. The medium power example has a 1 minute latency. And of course, in the high power latency, it's milliseconds. So there you go. I'm happy to take some questions. Covered a lot of ground here tonight. I hope you've enjoyed it.
At this time, if you'd like to unmute and ask Walt a question. Oh, here we go. Sorry. Question, how reliable are the off-the-shelf platforms such as made by Maxim? Their off-the-shelf development bands claim to have algorithms optimized for SpO2 measurements on the wrist. Are these reference designs and algorithms reliable?
If you're going to make a measurement with a PPG sensor, you're probably going to use one of these chips. The manufacturers have done a good job of making a chip and providing algorithms that make these measurements, but they haven't done the whole thing. After you make your PPG sensor, it needs to be calibrated with people. So you've got to actually try it on different people, collect data, and make some calibration adjustments. So plus you've got software to write, you've got the board to design, but it is a big help. Doing a PPG measurement is much easier today than it was 10 or 20 years ago.
Other questions for Walt? Well, that was quite a bit of material in terms of the power consumption, the strength of the radios, the nature of the power budget across it. Looks like 4 or 5 orders of magnitude between distance and bandwidth.
Yep, but what I find really fascinating is that NB-IoT and LTE-M, they can send directly to the internet without a cell phone. And now that they reach most of the population, nearly all of it, we're recommending people consider that in designing devices. I expect you're going to see it a lot.
We had a question perhaps from somebody who's in a contest with others. Why are the step counters on watches so inaccurate?
Well, you know, you're measuring steps with a device that's mounted on your wrist. And despite all the algorithm work that they've done, your wrist motion isn't always related to your steps. It does tend to be if you're running, your wrist moves along with your feet. But when you're walking and talking at the same time, you may be moving your arms in a very different way. So it's very challenging. And in most cases, if you got a 10 or 20% error, you may not even notice it. But I suspect that we have a bunch of engineers here who would notice things like that.
Can you comment on the processor power? There was a company at a compute that was doing asynchronous processors. I think they kind of got out of the low power stuff and went for AI instead.
This is a huge topic. There's so many different processors with such a range. There are processors that consume microwatts. Their capability is limited, but you know, for many cases, that's exactly what you need. And you can even turn them off most of the time. So you can have devices that consume microwatts and use a coin cell and last for years. Unfortunately, some of the sensors aren't such low power. So for a practical device, if the processor's in the microwatts, it may not help a whole lot if the sensor's in the milliwatts. And the wireless transmission may be in the milliwatts or high microwatts.
Is there anything in the millimeter wave bands and license bands? Sensor stuff?
Well, oh, you mean a sensor that's using millimeter waves? You're not talking about 5G?
Not 5G particularly, no.
There are all kinds of sensors. Yes, there are sensors that are a lot like radar that will take an image and measure motion. But when you're in the millimeter wave range, this is not low power. So they're not used on wearable devices.
Mm-hmm.
Would you name some of those processors?
I'm afraid I can't give you processor numbers. If I knew them, I can't remember them off the top of my head.
That's fine.
I'm not current in the circuit design.
I have used MSP 430 from TI for very low power
MSP
measurements.
430 has been a standard for low power. There are processors now that are far lower, but you know, the 430 is one that a lot of people know. And if you're not trying to get down to microwatts, it's fine.
Well, Walt has expressed some interest in doing we're going to try and do the traditional PATCA networking rounds as a closeout. So I'm going to stop recording.